Well, thank you very Dennis, for the introduction and invitation to be here. I think the last time I gave a lecture at Stanford was something in the 90s. So it's always a pleasure and a great honor to be to this university. So the story I want to tell you has been around for a while, and actually quite a few YouTube versions of earlier versions of this talk. I don't know how many of you have seen it or heard about it, but I promise some new things here. Now, this is a colloquium, so I have to be clear to everyone. First of all, this is, as you see from the title, there are essentially two themes there. One is information theory, and the other one is learning, or in particular, what we call deep neural networks. And in between, there is this bottleneck, which I'm going to describe. But essentially, as you may know, I mean, deep learning is one of those things that change the world. I think we can say today without exaggerating too much. So neural networks have been around for a long time. Or the idea, starting actually in the 40s, with the formal idea of a neuron as this, what we call the McCulloch-Pitts neuron, which is essentially just this gate, which is to take a dot product of some weights by some inputs and then pass them through some sort of nonlinearity, which originally was just a sine function and then was softened to some sort of a sigmoid function. And then today we're using all sorts of other functions, mostly what we call ReLUs, essentially just rectifiers, linear rectifiers. Now, the idea of actually putting them in networks with many layers is quite old. It goes all the way to the 50s through the work of Frank Rosenblatt, essentially, who also termed the notion perceptron, or multi-layer perceptron. And this was essentially, when you look at his book from 1959 or something like this, it has all the story in it. I mean, the idea of actually putting many layers of these nonlinear threshold functions connected to each other as some sort of a pattern recognition system. Nobody was talking about learning then, but it's there. But this was ruled out as not practical in the standards of the 60s and 70s, having too many parameters, highly nonlinear, impossible to train because you're going to get trapped in local optima. All the good stories that we all know how to tell our students, that too many parameters, it's not going to work. And it was essentially ruled out in a very bright, brilliant book by of Minsky and Papert, two really important names in the history of AI, who gave us completely rigorously, by the way, all the good reasons why it will never work. Now, it came back in the 80s through what we now call the connectionism era. When I actually got interested in these things after finishing my PhD in physics, in nonlinear dynamics, actually. And then I went into this story of physics of neural networks, which emerged actually from the Hopfield model and a few other things that came in the early 80s, 82, both the formal definition of machine learning through the work of Les Valiant, which was later on connected with the works of Vapnik and other Russians who were there even before. And it was actually Vapnik who killed the idea at the end of the 80s and early 90s by essentially introducing this notion of kernel methods and support vector machines, which are some sort of neural networks, but they are simpler and much easier to analyze and prove things about them. And for about a decade, they really dominated the machine learning field in the 90s. During the late 80s, by the way, some physicists, including me, started to do something which we then call statistical physics of neural networks, which is essentially analyzing large scale, I mean, in the thermodynamic limits, in some sense, networks like this. But what we could do is really show off our mathematical techniques on very simple toy problems, like one layer perceptron, in some cases 2 layers, a 3-layer system which couldn't really do anything interesting using these methods. And of course, the whole idea of using this large-scale statistical physics was essentially didn't leave a mark. I mean, it was unnoticed. Some physicists still like it, but it didn't make any big difference on the machine learning community, at least. But then, during the last decade, and since the late 2006, 7, 8, 9, a certain group of people, I'm sure you all know about them, Jeff Hinton, Yann LeCun, and a few others, essentially pushed the idea of neural networks to what they called, or we call now, deep neural networks by adding many, many layers. And the number, and of course, it's not only the number of layers, it's the size of the problem, especially the size of the input, which grew up by 3 orders of magnitude, sometimes more, 4 orders of magnitude. I mean, so we moved from inputs of the size of hundreds, let's say pixels of an image or something like this, to megapixels or sometimes more. And we are now talking about problems which are really large scale. And with it came this big surprise that around 2007, 8, 9, those deep neural networks with a lot of layers started to beat all the previous technologies in competitions on image recognition, object recognition, speech recognition, a lot of other problems in signal processing, later on in control, in networks with feedbacks and so on. Essentially, they took over almost everything we used to call AI. I mean, both vision, speech, natural language processing, playing Go, playing Atari games, whatever you want. Essentially, whatever you want. It's really very surprising because it's essentially the same architecture. Many layers of these nonlinear threshold gates, which essentially somehow miraculously solve many different problems. And of course, they are also inspired by the brain in various ways. I mean, we call them neural networks because there's some sort of resemblance or analogy with the way we understand the neural system, but the resemblance is very weak at best. So the question, this was actually very bad news for theoreticians or people like me who really try to understand why these things work so well. So I'm going to start slowly because I'm going to just lay the foundation. But so during the last 5 years, essentially, together with 2 students whose name was mentioned there, Noga Slavsky and Ravid Schwartz-Ziv, both brain science students actually in Jerusalem, we started to explore the connection which means something which I essentially thought of in the 80s in the context of speech recognition. I mean, a principled information theoretic way of extracting relevant, small dimensional relevant variables from large complex data, which later in the 90s we called the Information Bottleneck method. I'll come back to this. And I had a very strong feeling that this is the right theory or the right way of understanding why these deep neural networks work. And of course, this was largely ignored as well for a while. But then we started to do some experiments and some simulations, and I started to give some talks which are on YouTube. And in the last year, the whole thing, there was some sort of face transition. Everybody somehow see this picture. And I'm invited to many places, including Stanford, to talk about it. So this is something which for me was very, very nice, but quite a big surprise. So what is really this story? So it turns out that we are really combining 3 different ingredients, which in a sense change the paradigm, first of all, about learning theory. So in learning theory, what I call rethinking learning theory, we actually move from what we used to call distribution-independent bounds of the type of the PAC, the probably approximately correct model of Valiant, which essentially gives you bound on generalization error, which are independent of the distribution. It means independent of the problem, but are very strongly dependent on the architecture, on what we usually call the hypothesis class. I mean, what type of functions my machine or my algorithm can generate. So we move from this to a different type of bounds, which are actually strongly sensitive to the problem. They're problem dependent, they're distribution dependent, but they're much less sensitive to the architecture. So I moved the universality from the problem or the distribution of the problem to the architecture that learns it. So from worst case distribution dependent results, we move to typical case distribution dependent but architecture independent results. And I believe that this is very important for this type of machines. the worst case analysis doesn't seem to get us anywhere. This I do by actually using all the ideas that are just rethinking about information theory or the Shannon's communication theory in a slightly different way. So using the same techniques or the same mathematics that is used in information theory, which is the notion of typical sequences or typicality of very large patterns. I'm reusing it, but the typicality here is not in time, but actually, let's say, in the patches of the images that we train, or in pieces of speech, or whatever the signal is. I take into account the fact that it's really big now. Because it's really big, we can use those typical average arguments and actually get very precise results. So this is the way information theory comes into the game. But information theory is not going to tell us much about the most important aspect of this question of deep neural networks, which is the fact that we actually can train it effectively in finite time. I mean, in hours or days or weeks, but not in tens of years on our computers today, which means that there's something that scales very nicely with the size of the problem without paying exponentially long times. Now, so time is a different issue, which is really the computational aspects, and it's not going to be answered by information theoretic ideas because information measures are invariant to computational complexity in a very profound sense. So what comes, then the third ingredient here is really the stochastic dynamics of the training algorithms we're using, which is what we call stochastic gradient descent, or backpropagation, or error backpropagation, or all these kind of things that we are using for deep neural networks. And those algorithms turn out to be not so stupid as we used to think. I mean, this is exactly what Minsky and Papa told us that it's never going to work. Actually, they work miraculously well, and any attempt to improve them, let's say by moving to things like second-order methods, or methods which are not just sliding along the gradient, or in a noisy version of the gradient, tend to usually don't work well, or actually don't work at all with this type of large problems. So the question is why? So I'm actually going to connect all these three things. Let me skip this. So essentially, the idea is simple, and I just want to establish a few facts that I apologize for those of you who may have seen it elsewhere. So I'm going to think about the neural network. Remember, this is each one of those circles is a neuron, which means a linear threshold gate. And now think about the input layer, let's say pixels of an image or something like this, as a very high entropy variable, a very high dimensional variable, which I call x. And think about the label. So I'm now talking about the simplest possible form of deep learning, which is supervised learning. I'm showing the images and give, let's say, is it you or not you, or is it a face, or is it a car, or is it a dog or a cat, or very simple classification problems. Now, so I can actually think of y, the desired label, as a very simple variable which can be only just one bit. Anyway, it's a lot simpler than x, okay? The problem is that this one bit is not encoded in any simple way in the image. There's no one pixel or one bit in the image that tells me this. It's highly distributed. So what actually happens in neural network is that this input, or this first layer, is now going through a transformation of layers, and each one of them is a new representation of my image. And just by looking at it, you see that there's a Markov chain of representations here. So each representation can be calculated only from the previous one and affects only the next one. So the story I want to understand is what's actually going on through this representation transformation, or this cascade of representation changes. Now, before I go on, I must introduce some quantities, which I'm sure if you are mostly electrical engineers, you all know them. So I need some information measures. In particular, I need the notion of mutual information. So how many of you don't need it? Know what mutual information is? Not that many. At least you don't dare to say that you do. That's strange. Okay. So I need two quantities. One of them is known as the KL divergence, or the cross entropy, or the information divergence. Or it has many different names. And this is this average log likelihood of two distributions. So I have P and Q over some random variable, take the log of the ratio, and average with respect to the first one. This quantity is non-negative. It's 0 precisely when they're equal almost everywhere, and it's a very fundamental quantity which I can teach a whole course about why it's important in so many different ways. But anybody knows something about statistical hypothesis testing, for example, know that the log likelihood ratio is a very important thing, and the average of it is really telling us a lot about the rate of making decisions, and so many other things. Of course, it has entirely different ways, meaning the information theory. The mutual information, which I need all of you to appreciate and know at this point, is the KL divergence between the joint distribution of two variables and the product of their marginals. And it's going to be 0 precisely when the two variables are independent. The joint is the product. And otherwise, it's a non-negative quantity, which can be interpreted as the entropy or the uncertainty in the variable x minus the uncertainty removed from x when I know y. This is a symmetric quantity, and it's actually going to be very important for us, because I'm actually going to, from now on, I'm going to look at mutual information quantities in my neural networks all over the place. Now, there are two things about mutual information that I want you to appreciate. One of them is known as the data processing inequality, which means that if I'm moving along a Markov chain, let's say x, y, z in this case, then information can only decrease. This is true not only for mutual information, it's true for a whole range of other measures like this, but there's something very special about mutual information, which is uniquely determined, not only the data processing inequality, it has another property which I need, which we usually call the mean as minimizer, and I'm going to need it, but I'm not going to talk about now. So of course, an immediate consequence of the DPI, the data processing inequality, is that under any invertible maps of x and y, the information doesn't change. So this is actually the bad news for anybody who's trying to use information for computational complexity, because it means that I can encrypt I can take any hard transformation, how to invert transformation of my data. This is not going to affect information measures, but it's going to create a big headache in terms of the computational complexity. So information is not telling us anything about computational complexity. But now if I look at my neural networks, there is immediately a chain of inequalities which I want to call the information path, which is essentially how much information is there at layer 1 about the input, how much information is there in layer 2 about the input. And because it's a Markov chain of transformations, information can only decrease about the input. And if I ask the same about the desired output, remember I'm talking about generalization, about what the label should be, not what the label is at the end of the network, this is also decreasing when I go through the layers. So I have these two chains of inequality, which I'm going to call the information path of a network like this. And essentially, what you should appreciate that only this Markov chain of layers are essentially inducing some sort of partitioning of the data. So if you think about all the images that are mapped to the same value of the layers, the same representation of the units, and this partition can only get coarser when I move from one layer to the next. So there's some sort of coarsening of the representation. So this in information theory, this is related to something we call successive refinement. I'm going to come back to this at the end. But notice that, of course, I can scramble, or the network can scramble my representation in an arbitrary way, and this will not affect those information measures. OK, so another slightly different way of thinking about it is to think about each layer as being encoded by some sort of, so there's a map, a stochastic map in general, from the input to the layer. Here I call it T, it was the same thing. So any layer T, T1, T2, T3, any one of those hidden layers is actually a map from the input, which I call the encoder of the layer. And so any layer has an encoder, which is how it is mapped from the input, what type of maps it generates. And there's a decoder, which is the way I'm trying to extract the label, or the desired label, or this is the label I'm actually training. I call it y hat here, because it's not exactly y. This is what the network is generating. And during the training, two things happen. First of all, I'm trying to push y hat to be as close as possible to y. Then I said that the network is working well. And the other thing is that when you move from one layer to the next, the encoder becomes more and more complicated. The first encoder is very simple, but the decoder is very complicated. And then the encoder becomes more and more complicated, and the decoder becomes simpler. At the last hidden layer, the decoder is essentially just a linear threshold function, or just a perceptron. just a one-layer perceptron. Okay, so the question is, how is this miracle happens that somehow from layer to layer, I capture more and more information by the encoder and eventually get to a very simple decoder. And now, here is a very informal formulation of a theorem, which we now have a much clearer formulation. And I dare to say that essentially, there are only two numbers out of those zillion of parameters that are really important for each layer. And this is the mutual information of the encoder and the mutual information of the decoder, or essentially the mutual information of the desired output given the layer. And I argue that if we know these two numbers, for each layer, and in particular for the last hidden layer, we can predict both the two things we really care about, which are the accuracy, the probability of making an error outside of my training data, what we call the generalization error, and the number of samples, or what we call the sample complexity. So the trade-off between complexity of the samples, how many data I really need, and what accuracy this is going to give me, is going to depend for large enough problems, where I can use typicality arguments, and for large enough networks, such that they can actually learn this rule, it's going to depend only on these two quantities, the information of the encoder, information of the decoder. So this is quite remarkable, because it's going to simplify the problem dramatically. If you actually believe me, then I don't need to know anything about everything else. The architecture is not so important. I need to know only how much information there is in the encoder of the decoder of the layers. Now, this is what I call the information plan. Sometimes we call it so these two coordinates, the information about the input versus the information about the output or the desired output, are going to tell us a very interesting story. So in order to see this, I'm going to use this movie that some of you may have seen, but it's always very important to see it again. So what you see here are these two axes. The x-axis is the information that each of the layer has about the input. The y-axis is the information that this layer has about the output. And the colors represent layers of a specific neural network, which I trained 100 times with different random initial conditions and different training data. And I changed both the sample size, it's the same size, but different selection of the sample, and the ordering of the examples, because it's a stochastic gradient descent which I'm going to train. So other than that, I'm now training these deep neural networks in the most plain vanilla using TensorFlow or something like this, a way like everybody else. And what we want to see is how those information values evolve in time through the epochs of training. So what you see now is the initial condition of the network. So right up here in blue is my first hidden layer. This first hidden layer essentially maintains, even with random initialization, almost all the information about both the input and the output. That's why it's hid. So this is the first hidden layer, the one closest to the input. And the last hidden layer, this one in orange, is the last layer which is supposed to learn. You see that the initial condition, they know very little about both the input and the output. So they're in the left down corner. Now, this is the initial condition. What happens when you start training it with stochastic gradient descent? And so this is usually the picture which wakes up everyone. So essentially, what happens, and then you see there the number of epochs running up there. So it was very fast. So I'll do it. I'll move it slowly. So essentially, up to this point, which is about 300 epochs of training. So what we call epoch of training is essentially cycling of all the examples in mini batches. And the way we calculate the gradient in stochastic gradient descent is we don't calculate the gradient over all the examples. We actually cut the examples into small sets, which we call mini batch, which can be 100 or 200 or 300 examples. And we calculate this noisy version of the gradient, and we update the weights for each one of those mini batches. So any update of the weights through all the mini batches is what we call epoch. So after 300 epochs, which means 300 cycles of cycling of the data through my networks, we get more or less to this point, which is interesting. So first of all, you see the data processing inequality. You see that the information goes down, as you expect. Actually, at this point, they're almost linearly down, and you see there are actually 6 hidden layers. The reason you see these clouds is because, as I said, we repeated the experiments 100 times with random initial conditions. But so up to this point, around 300 epochs, all the network, all the layers went up, which means they increased the information about the label, but also to the right, which means they also acquired more information about the input. All of them, all the layers together. And from this point on, something interesting happened. It starts very, very slowly. I'm sorry. It's very, very slowly moving to the left and up. And if you look at the number of epochs, out of this about 10,000 epochs, only 300, which is very little, it took to get to this middle point, which I argue is a very important point. This is where the training error essentially is saturated now. It's very small. This is what we all believe is the most important part of training, fitting the labels of the data. But this happens very quickly after around 300 epochs. And then the rest, 10,000 minus 300 epochs, are essentially slowly moving by what I'm going to call diffusion, or by the noise in the gradients. Of course, there are still gradients. There's still something that's pushing you down, but it's dominated by the noise in the gradients. That's what I'm going to show you.
What do you think is slow?
Well, it's slower relative to the fast. I mean, it's 10,000 epochs. I
understand, but why? Is there any information theoretic reason why it should slow down?
No, everything will be clear at the end. Okay, okay. I hope not everything, but some things. Okay, so there are these two what I call phases of learning. In the first one, you fit the data. In the setting down, you do this very relatively slow. I mean, it's 10 or 100 times slower than the first phase, where you move to the left, and I call it the forgetting phase of the learning. I'm already going to give you the gist of the story. During the first part of the learning, you actually fit the labels. You do this, what we call empirical risk minimization, which we consider the holy grail of learning for many, many years. This is what we want to do. But it's actually the second part, which is done when the error is essentially fluctuating. I mean, it's not zero, but it's moving up and down between those many epochs, which are subsets of the training data. During this phase, which is not supposed to do much according to the classical theories, most of the improvement in my information about the label happens. And this is strange. I mean, this requires an explanation. And my story is that the gist of it is, at this phase, we actually forget or learn to ignore the irrelevant details of the patterns. Those things which are not labeled, the changes, the differences in the background, the fact that there are so many dimensions of the problem which are not important for the label. So that's the hard part. Ignoring or forgetting or learning to ignore the irrelevant details of the problem. Now, so the rest of the story is just trying to justify what I just told you based on some other analysis. Yes?
Is there some easy explanation for how one goes about calculating mutual information in these high-dimensional?
Yes, I'm going to tell you. Just be patient. Okay, this is the story. So anyway, this was, some of you know, I mean, this story attracted the Quantum magazine, the attention of Quantum magazine. This is a nice picture that they gave for this. So actually, there are several other questions I wanted to ask before going to this. So just looking at this picture, first of all, you want to ask, is this the general picture, or maybe just this is a special case with a very special network and a very small problem and so on. So believe me, we see this precisely the same story for very large problems, or at least as large as we could. The second question that usually people ask, how do you estimate mutual information? Okay, so we estimate mutual information using, in this case, a very small problem, and we bin the data. For large problems, we use a much more sophisticated methods, all sorts of parametric representation like Gaussian mixture models on each one of the layers. We know how to do it. If you do it wrong, you don't see this picture. Actually, there's a very nice paper came from Harvard, was actually attacking us precisely on this. This is not the issue. Now, so we see, the second question is, which at least for me was very interesting, among these 100 points, why do they concentrate? I mean, why do you get this relatively concentrated points? I mean, so this requires an explanation. I mean, these are entirely different networks. If you actually compare the weights, there's no correlation. They look very different. Or you compare even the values of the neurons, They are not correlated, but the value of the information turn out to be very, very sharp, and it gets sharper the larger the problem is. This is precisely what we like. When things get concentrated in the large limit, then we know that we have what we call good order parameters. Now, the third question is, okay, what do these numbers mean? I mean, why they are interesting? So I already told you that the y-axis is going to dominate the generalization error. The higher the information about the label, the smaller the error, and this is a rigorous statement. It's not an approximate statement. We can prove it, and it gets tighter and tighter bound when you get to larger problems again. The second, the x-axis, or the amount of what I call compression, I mean, how much I forget the input in bits, is precisely going to dominate the number of examples I need, or the sample complexity. So this is why this is the theorem that I mentioned in some sort of a coding theorem, because it's relating informational quantities, those entropic-like functions, to real things we care about, like code lengths or errors, or in this case, generalization error and number of examples. And that's why this is in the flavor and the spirit of what we like and love about information theory. Now, so the third, of course, and the last question here, which is the most fascinating one, is what governs this strange dynamics? I mean, why does it move so quickly first and so slowly later, and why does it compress? So I want to answer all these questions to you. Of course, not completely, as much as I can. So again, because they concentrate, we can average those trajectories, and this is the simple version of the story. I now average those points, and you get this very nice trajectory. From A to C, I remember, I fit the data. From C to E, I generalize. And it happens that all the layers are doing this type of story more or less together. And they all come to this inflection point, point C, more or less together. Okay, so what is the story? Now, I hesitate to give you this proof again, because it takes time and it's rough. I mean, it's not as rigorous as I would like it to be, but I just want to give you the gist of it, as we like to say. So those of you who know something about learning theory, I hope all of you know something about learning theory, should be familiar with what we call what I call the old type of generalization bound. Let me eliminate I can't. So the old type of generalization bound looks like this type of bound on the left, which is essentially, and let me just magnify. So this is the generalization error, which is this epsilon, which is again the probability of making an error on my new unseen data out of my training, is bounded by essentially two terms. The number of examples, which is in the denominator, which, okay, the larger the number of samples I've seen, the smaller the error. But on the numerator, which is the important term, is the log of the cardinality of my hypothesis class. This is valiant. And this is beautiful, because it gives us bound, which is completely independent of anything except these two numbers. Of course, there's this log 1 over delta, which is what we call the confidence. And the confidence is this the probability of seeing a very bad sample. Okay. The probability of seeing a very bad sample is 0 when you talk about 1 million images. Once you move to very large data, this is completely negligible. For small problems, it's important. But we still keep it there. I mean, log of 1 over delta, think of delta as 10 to the minus 10, or something like this. So this is 10, okay? But we're talking millions of examples. So log of H and M are order of millions. Now, so it's the competition between the log of the cardinality of the hypothesis class and the number of examples. One is controlling the complexity of my learning. The other one is controlling the data I actually gain from the data. And of course, what we usually do is we want to work with the infinite classes. So we approximate, we cover the hypothesis class, which is usually infinite, like rectangles or things like this, by what we call epsilon grid or epsilon quantization, which essentially cover it with a finite number of points which are not more than epsilon apart from any other hypothesis, and find a grid like this, an epsilon net or epsilon grid. Now, usually if you have a finite dimensional system class, then we can cover it. The size of the cover grows like 1 over epsilon to the dimension of the class. This is geometry. So this can be the Hausdorff dimension, or the fractal dimension, or the VC dimension, or the fat shattering dimension. There are many different types of dimensions like this. They all behave like this. Eventually, when you need a dense cover, the size of the cover grows exponentially with the dimension. So if you plug this here, and this is really the miracle of the VC theory, if you plug this in the first time, you get that D over the number of examples is the dominant factor. Once the number of examples is larger than D, you essentially begin to generalize the dimension. As long as it's smaller than D, you don't generalize. This doesn't mean anything. This is beautiful. We have been working with this for 30 years now. There are many books in there, but the problem is that we all know, although some don't admit, that these bounds don't give us anything. They're vacuous for deep learning, which means that any reasonable estimate of the dimensionality of the class give us something which of the order of the number of weights, maybe the square root of the number of weights, maybe the weights log the number of weights, or something like this, but it's the number of weights depending on how you exactly count it, which is millions, or actually hundreds of millions or billions today. Whereas the number of examples, okay, some of them, Google told me yesterday that they're doing also billions of examples, but then they're talking about hundreds of billions of parameters. So there are at least 200 or 300 order of magnitudes between the number of examples and the dimensionality estimated in any reasonable way of this deep learning thing. Now, this is telling, to me at least, this is not the right theory. I mean, it doesn't work. Of course, there are a lot of good, clever people who are trying to estimate the dimensionality and to show you that this neural network is actually very expressive, that they can express extremely complicated functions, which is, of course, true. But this doesn't explain why they are performing so well with so little data. There must be something which regularizes the problem in a very profound way. So what I'm saying, essentially, it's the essence of it. Instead of covering the hypothesis class, let's quantize the input. So this is, again, for engineers, this is a very well-known story because this is exactly what we do in sampling. I mean, think about Nyquist, I mean, about band-limited functions. We actually, in order to estimate the function, we need to know it in a very small number of points. I mean, it is only in the Nyquist frequency. So most of the points we actually don't know their value, and still we estimate the function pretty well from samples. Okay, because the functions are clusterable in some sense. So the general notion here is take the class of patterns X and cover it by sphere. So X here, this ellipse, blue ellipse, is all my patterns, all the images that I care about. And now imagine that I can group them or cluster them somehow or partition this data into cells which are essentially homogeneous with respect to the label, which means that the probability of having the wrong label in each cell is smaller than epsilon. How I get it, this is a different story. But let's say that I gave you this partition, then I know that the number of functions go from, let's say, Boolean function, from 2 to the cardinality of X to 2 to the cardinality of the partition. Now, okay, so this doesn't look like a very dramatic thing, but now I go to information theory. And again, I'm going to skip all the notion of typicality. Do I need to remind you what it is? Okay, so we are talking about typical patterns now, and I actually need it. And this is where the heart of information theory comes into the story. Typical patterns are patterns where the probability of a pattern can be approximately factorized into a long product of conditionally independent terms. So this is the story, let's say, with hidden Markov models, or with Markov random fields, or with Bayesian networks with some finite degree, or with a physical system with Hamiltonian with finite interactions, and so many other systems that we know, that essentially the distribution can be written as a product or approximately asymptotically as a product, dominated by a single product. In this case, the log of the probability is going to approach a limit. And this limit is known as the Shannon-Macmillan entropy. So if, and this is of course the limit in probability, but we know that if such limit exists, the system has a well-defined entropy. And at the same time, almost all the patterns, because this is going to concentrate to this limit due to the central limit theorem, eventually, when n is large enough, most of the patterns are going to be very close to this limit, which means that most of the patterns are going to have the same probability. And this is a property we called in information theory asymptotic equipartition. think this name is actually due to Tom Cover, but I'm not sure. So it's this particular number which tells us all typical patterns, not only almost all patterns are going to be typical, but all of them are going to be essentially equally likely. Which means that the size of the number of typical patterns is essentially 1 over this probability, which is 2 to the entropy. Okay, so this is the fundamental trick that is used in information theory in both source coding and channel coding. And I'm going to assume that my partition is such that the pattern associated with each of these cells are also typical. So this is, again, I divide my inputs into cells, the same way that I divide a glass of water into little drops, which are all in equilibrium. And the same trick exactly that works in statistical physics works here. And in that sense, I assume not only that the pattern itself is typical, but the conditional on the partition is also typical, so I can write it as 2 to the minus conditional entropy. Now, this is, as I said, it's a very familiar trick, but it's still very important here. So what I do now is that I can estimate the cardinality of my partition using information. It's essentially the size of the typical patterns, 2 to the h, divided by the average size of the typical cell, which is 2 to the conditional entropy, h x given t. So this is the cardinality of the partition. So now we plug, so the cardinality of the partition, again, is this one, 2 to the information, because it's hx minus hx given t, the same reason it appears in information theory. But now it means that the number of functions is 2 to the information, because I have another exponent there. Now this is tricky, although not terribly surprising when you think about it. I get this type of bound. The bound is now that the generalization error is bounded by the exponent of the mutual information between my representation and each of the layers, divided by the number of examples, which means that any bit of compression of the representation is equivalent to doubling the data. This is an exponential improvement in the bound. So essentially, if I compress as the layers seem to be doing in this phase of compression, I actually compress the representation by k bits. It's like doubling, multiplying my data by 2 to the size of my data by 2 to the k. Okay, so I argue that these bounds are much more realistic. They actually tell us if you actually look at the value of the information. Of course, those of you who are a little more familiar with learning theory know that, so essentially this bound becomes interesting when the information is essentially of the order of the log of the sample size. Now, the log of the sample size is precisely the minimal number of samples which I really need to label if I could choose them carefully. This is the minimal number of queries. So rather than having randomly labeled sample, I could, if I choose the labels, I could settle for this log m. And this is precisely the classical sample complexity, sample compression results of Manfred Warmuth and a few others from the 80s. So we know this is not really surprising. What is surprising is that the network is actually minimizing this information, and this is happening through diffusion. So, okay, so now I move to the last part of the story. Or actually, it's the second part of the story. So, okay, so I hope I convinced you that this information plan is interesting. First of all, you see the interesting dynamics. Things concentrate somehow in a very nice way. So the question is, what is the bound, the maximal value of compression that I can achieve for a certain number of bits of information? So this turned out to be a question we asked a long time ago. So I asked it in the context of understanding what is a minimal sufficient statistic. And the minimal sufficient statistic is, as you may know, is the simplest function of a sample that capture all the information about a parameter of a distribution. This is the classical definition. If we don't think about the parameter, we think about the label as the thing we care about. So I want to compress my data without losing information about the label. And the way we do it is essentially by solving a constrained variational problem, minimize the mutual information between x and the representation, which in this case I call x hat, because this is the notion used in information theory and distortion theory. It's just a coincidence. And so minimize the information to the representation subject to constraint on the information on the label. Now, this looks like a tricky problem. It's actually solvable. And we solve it by essentially an extension of what we call the Blau-Torimoto algorithm in information theory, or essentially it's an iteration between the encoder and the decoder alternately, and these iterations converge. We know how to prove it almost always, except some very important critical points on the curve. And they give you this interesting limit. So essentially, there is in this plan information about the output, information about the input. There is a line, this black line, which is the rate distortion-like function, which tells you above this line there are no representation whatsoever. Below this line there are many, and the optimal representation are exactly sitting on this line. Now, this if I have all the data. So in principle, our first intuition was, this is something we wrote in 2015, is that if nothing else stops the network, the layers should somehow converge to this line. There was absolutely no reason for saying that. But I said, okay, if they work so well, maybe they're optimal in this information theoretic sense. Now notice that this is precisely the bound I was talking about. This is a distribution dependent, problem dependent bound. But the bound is universal for any architecture, whether it's your computer or your brain or an alien from another galaxy. Nobody can do better than this bound, okay? So this is the absolute bound on this problem. Now, the real problem that I really always need to emphasize is that you don't have infinite data, unfortunately. We always have a finite sample. And if you have a finite sample, we actually cannot reach this black line. We reach a very different bound, which is this red line. Which means if I'm using a very little compression, a very fine partition of my data, I will not generalize because most of the cell will be empty. I will not see enough labels to actually fill my cells. So in this case, I'm going to get a very poor prediction of my label from very fine partition. On the other hand, if I compress too much, then the black line hits me, and I simply cannot generalize. So there is some maximum somewhere here where I want to be with finite samples. This is the best you can achieve with finite amount of data, and this is a rigorous bound that we know how to calculate, again, only from the problem and the number of random examples. Nothing else comes into this game. So the argument is that indeed the network are somehow fitting this, pushing the last layer into this region. Now, in these pictures, I highly exaggerated. I mean, in reality, the black line is a lot closer to the line, but it's still there. And the red line depends, of course, on the sample size. So there are two types of losses we need to work on. One is what I call the compression loss, due to the fact that I actually compress the representation, which is this, the first bound. And then there is the finite sample loss, which is the difference between the red and the black. And I want to minimize both of them. OK, so now so here is just to give you a flavor of what happens when you train with finite data. So it's the same problem, the same old small network. But again, I argue that this is the general picture. We see it in all problems. On the right, you see training with a lot of data. In this case, 80% of the data, this one. So you see, again, there is this trajectories of the layers. Remember, I'm talking about the information plane, information on input, information on output. And you see this very fast convergence to this green line, which is what I call the inflection point, where there's a sharp transition in the behavior of the gradients. And I'll show you in a minute. And then you see that there is this slow convergence. You see that all the layers shift to the left. And you see this by the number of epochs here is the color. And you see that the color is yellow for very high number of epochs and is blue for a very small number of epochs. And you see that indeed they slowly converge to some points. On the other hand, if you train them with small data, this is only 5% of the data, you get the same initial phase. They fit the data very well, but then the information through the compression goes down. So this is something which we may call overfitting. It's not overfitting, it's actually overcompression. I mean, you are simplifying your representation beyond what you are actually allowed to do by the data that you're given. So you cannot keep the homogeneity of the cells with respect to the labels because you don't have enough data. OK, so, and you see somewhere in between is somewhere in between. So of course, the nice thing is that we actually have a theory for this line. And this theory is, again, data dependent, but model independent. OK, so just to understand what happens, look at the same video again, but this time at the bottom I show you the training error. Actually, it's a generalization error, but it doesn't matter. They look very similar. And you see that the first phase was essentially changed exactly when the error got into this knee, where it's essentially saturated. So of course, when the error becomes more or less constant, it's still going down, but it's very slowly going down. You see that the gradients are going to be smaller because the error is small. But now the mini batches, the difference between the training on some examples and other examples of these fluctuations start to dominate the story. And indeed, this is the picture I really like to show. So what you see here, this is actually the network we use, but as I said, this is not, it's important only in one aspect, that the layers get, the width of the layers gets smaller and smaller. So this is some sort of an Eiffel Tower. If I use the different architecture, I'm going to see a different type of behavior in the plane, but the gist of it is that the last layer is doing something very, very similar. So what you see here in different colors are the mean of the gradients, I mean those solid lines, and the broken line are the standard deviation of the gradient per weights in every one of the layers. And what I want to emphasize, and actually it turns out that we are not the first to see this, so this is well established, that there are actually two clear phases of the training. In the first one, you see that the gradient is much larger than the standard deviation. This is what engineers like to call high signal-to-noise ratio. This, by the way, is a log-log plot. So the difference in log is the log of the ratio. So this is a log signal-to-noise ratio. Now, so in the first phase, there's essentially 2 orders of magnitude difference between the fluctuations and the mean. This is what we call clean gradient, okay? On the other hand, when they reach this gray line, around 300 epochs, as I said, the gradient essentially saturates. It's not exactly saturated, but it gets to be very small. So the gradient, the norm of the gradient, is essentially the norm of the gradient in every layers squared, and you get that the gradient get down. There's also the sort of dispersion among the layers. The lower layers get a larger gradient than the smaller gradient than the higher layer. Never mind that. But what is really dramatic is that the variance jumps, and from this point on, essentially the standard deviation is much larger than the mean. So this is what you all call low signal-to-noise ratio, which means a very noisy gradient. So there's a very clear analogy, dual picture of the same story that we saw with information in the gradients. Actually, I think that I know that the gradients determine the picture. I can actually solve a Fokker-Planck equation using those gradients in order to propagate my probability distribution and show you that information indeed does this. So, but notice what happens here. There are actually 2 phases. One of them is also called drift. So those of you who know what the Fokker-Planck equation is, the Fokker-Planck equation has a linear term, which is governing the drift, and has a quadratic or second derivative term, which is governed by the fluctuations. If the linear term is larger, essentially you just move. The distribution just moves linearly. If the second term is larger, you are in a diffusion equation, much larger. So you're essentially dominated by diffusion. And it turns out that if my story is correct, that the diffusion phase of the gradients is the most important part of the learning. And you see that there is a diffusion phase. Actually, there are many, many details that I can see in this picture. For example, this peak is related to the fall into a very flat minima. And the fact that the difference between the variance and the mean in log scale is essentially constant is telling me that the log signal-to-noise ratio of the gradient is essentially constant when I approach the convergence, which is completely consistent with the Gaussian bound on the information, because the log of the 1 plus signal-to-noise ratio is the Gaussian bound on the mutual information. So there's a beautiful confirmation or reassurance of the whole story just coming from the gradients. Actually, what we do now is really solving the Fokker-Planck equation, the first 2 moments of the distribution using the Fokker-Planck equation, and we see exactly the same story without measuring information at all.
Going through the desert.
Yeah, going through the, whatever. Yeah. There are many, many other details. I don't have time to talk about it. By the way, so the story now becomes a little clearer. There are 2 phases to the gradient. Here you see the signal-to-noise ratio on the left here. So the signal-to-noise ratio has this very sharp drop. It's not really a phase transition, it's some sort of a crossover. And in this low phase, gradients are very noisy. In this high phase, gradients are very clean. In the high phase, I essentially fit the labels. In the slow phase, I essentially learn to forget the irrelevant details of the problem. So this is some sort of an unsupervised learning. I mean, because nobody, as I said, is labeling the background. But the fact that I see some pictures with this background, some other pictures with another background, is giving me a lot of information on what to ignore because there are fluctuations in the mini batches. And by the way, if you change the size of the mini batch, you see that these 2 points, the point where you you start to forget, I mean, this point, is exactly linearly related to the phase transition and the gradients. So and when actually, even when you train with a full batch, I mean, and some people do, I mean, let's say that I don't want mini batches. So this was actually done in another attempt to show that we are wrong. You train it with full batch and you get compression as well. But so if we do it with full batch, you see that the full batch is somewhere along this line. It's just a much, much slower compression. And indeed, even with full batch, there's noise. There's quantization noise in time. There's a noise due to all sorts of sampling error and so on. So this small noise is enough to eventually compress the representation. Now, okay, so we see this in many problems, and I just want to skip it because we don't have time. The gist of it, again, geez, I'm using this too often. Surprisingly or not, the layers in this problem converge to the optimal bound. So what you see here in blue is the information bottleneck curve, which I calculate using rate distortion using the Blau-Tarimoto algorithm, because I know the distribution of the problem. And what you see in red, those crosses, are the end point of the layers in this plane. And of course, we magnified everything. This is just the region between 0.98 and 1. So everything is just blow up of the top of the curve. But this is beautiful, because indeed it turns out that those layers form some sort of what we call a successively refinable code of the problems. And now it's an entirely different story why it happens. Okay, so why it happens, I'll give you just the very sketchy proof of it. Okay, so we know, I mean, what is it in this stochastic dynamics that actually put you to optimal compression? This is not something we used to have in information theory. I mean, nobody, as far as I know, is, of course, there are many random codes all over the place, but nobody is using noise. I mean, random walks, I mean, diffusion processes in order to compress. Maybe you should. So if you look at what actually happens, again, in a very sketchy way, there is a Langevin dynamics, which means the weights as a function, the time derivative of the weights is proportional to minus the gradient of the error. But it's not a clean error, there's some noise added to it. And the noise is exactly due to those mini batches. So this is a gradient descent or a gradient flow with noise. And we know that, for a long time now, that it is under some conditions, which are not true here, like convex energy surface or things like this, you're converged to a Gibbs distribution eventually, or to a maximum entropy distribution. So the stationary distribution of this dynamics is exponential in the training error. So this is known since the 20s, 100 years from now. Now, usually the convergence is very fast if you are indeed in a convex space. But you are not in a convex space, forget it. So actually there are, think about a very high dimensional space where only a few of them are relevant. Those are the features that actually change the label. Think about that in face recognition. So I know they did something in the eyes and the size of the nose and so a few other 20 features that you can, these are the relevant dimensions. And all the other million dimensions of the network are essentially irrelevant. So if you think about the covariance matrix of the noise, it's going to be extremely elongated, very small in the relevant dimension and very wide in the irrelevant dimensions. Now, is it good or bad? It's actually good. Because what happens is that you very quickly converge in the relevant dimension of the problem. And you stay there. This happens in the drift phase. But then in the diffusion phase, you essentially do a random walk in all the irrelevant dimensions. And this random walk is increasing the entropy of the irrelevant parameters. And I do it in every one of the million dimensions of the problem. So the fact that each one of them is just doing one random walk is average with the fact that another one is doing another random walk. So on average, you actually get this Gibbs distribution in the irrelevant dimensions. And as you know, the dynamics of diffusion, I'm sure you all know that diffusion grows like a Gaussian, where the width grows like the square root of time, okay, in flat space. Okay, so this is what we all learned in school, in elementary school, I think, that the diffusion grows like a square root of time. And essentially, this tells us that the time that it takes to grow the entropy is exponential in the entropy. because I forgot to tell you, the entropy of a Gaussian is the log of the standard deviation. So entropy grows like square root of time, but like log of square root of time, and time grows like exponent of the entropy. So this turns out to be quite interesting, because this gives us a completely new understanding of why the layers help you. And I'm going to finish with this. It's 1 hour and 5 minutes. I was told that I have 75 minutes. Okay, so essentially, this is really a beautiful picture. I really like it. So it's the same problem, the same specific network that I'm playing with all the time. But again, this is not specific to this problem. I train it once with one hidden layer on the top left, and then 2 hidden layers, 3 hidden layers, and so on, until you get to 5 or 6 hidden layers. And the remarkable thing about this is that when you look at the colors, okay, remember, yellow is 10,000 epochs, a lot of time. And blue, purple is very short time. So for the first layer, this one hidden layer, you see that it takes essentially forever. I mean, within 10,000 epochs, I didn't converge to a good solution. It's a very simple network. I know it can learn the problem. The problem can be learned with one hidden layer. Takes a very long time. Now, when I start to increase the network, move to 6 hidden layers, a lot more parameters, a lot more complicated, but you see it's all down in the purple. Essentially, very quickly, within a few hundred epochs, I converge to a very good solution. Good solution means high information about the label. So, surprising or counterintuitively, the larger the network, the faster the convergence. Okay, so.
At least in theory.
No, this is experiments. I mean, these are just, the theory has to come now. Okay, so this is what we see in simulations. Actually, so this is a small problem. We can actually compare these things. So there is some advantage to having many layers, and most of the advantages in this diffusion process, because we see that we get very quickly, even with one hidden layer, to the point of compression, and then it starts to slow. Okay, so let's think again about diffusion. So I told you that diffusion is actually a Langevin process, I mean, adding noise, and I converge to this Gibbs distribution. But think about, I just told you that essentially increasing the entropy of the width, so when I increase the width of the distribution in the irrelevant variable, this I can show you very specifically, you decrease the signal-to-noise ratio of the irrelevant variables, which means that you forget them. You don't transfer the information. The capacity of the irrelevant variables is decreased. This is just a Gaussian bound on the capacity. So how long does it take to actually increase this entropy? So we know that delta t is exponential in time. That's what I told you before. So for these flat irrelevant variables, the increase of entropy is very slow. I mean, it takes exponential time in every bit of compression. Okay, so this will take forever to compress 10 bits or something, yeah. But imagine now that I put in this train of a Markov chain, and all of the layers are doing parallel diffusion, because that's what I do. I add noise to all of them. So they start to push each other. So instead of having time which is exponential in the sum of those compression, but the compression is the difference in information between layer to layer, I move to the maximum actually of those terms, which is larger than the sum. So this means that there is some sort of a boost of compression because all of them move together. They really help each other compressing. So there is some sort of, it's like a train with a lot of engines. They move faster. Actually, it's not a good analogy, but it's a lot of train, just a linear increase. This is an exponential increase in time. Because I move from an exponent of a sum to a sum of exponents. Or actually, the maximum of those exponents. So this is a really very intuitive and very rough picture at this point of why the layers help you during this diffusion. They actually enhance the diffusion, and each layer only have to compress from the point that the previous one forgot already. Of course, this is not exactly true, because you see that the first layers don't forget everything, they forget only part of the story. Okay, so the next part of the story, which I'm only going to sketch and just, the interesting question is now, okay, so we understand quite a lot already. We know that it's the noise in the gradients which is doing the work for us. We know that it's doing it because it managed to decorrelate the irrelevant variables of the problem from the label. And this is a slow process because nobody is labeling it for us. So it happens because there are fluctuations, batch-to-batch fluctuations, because there's a variance in the background of the problem. The next question is, what governs the convergence of the layers? Where do they converge to? They seem to be, so this is actually where the layers end up in this plane, but not as a function of the epochs, but actually the function of the number of examples. And you see that it's remarkably consistent. So now I have a completely different story to tell, which I'm not going to do, what governs the location of the layers in this plane. It has to do with the structure of the problem itself, because now we map deep learning into information theory, and now we can use information theory to actually calculate things. For example, if there is symmetry in the problem, we can show that a symmetric problem can learn faster because the structure of this landscape, this energy landscape, is much simpler. What I want to show you, just to end the talk with it, is direct simulation, actually looking inside those layers using what we call multidimensional scaling, essentially. So I'm taking this 10-dimensional or 20-dimensional layer and project it to 2-dimension, and I run all the 4,000 inputs and mark the points in 2 dimensions, and if the label of the output is 1, I mark it with black, and if the label of the output is 0, I mark it red, and if it's somewhere in between, we mark it somewhere in between these colors. So essentially what I want to show you is the dynamics of the topology of the network. So this is the first hidden layer. And remember, in order for my theory to make sense, I need those partitions to be homogeneous with respect to the label at some point. And notice that, again, so you really see this really crystallization. I mean, red attracts red and black attracts red, and eventually you get this pepper and salt picture of clusters that some of them are red and some of them are black, and you see that the colors became strong, which means that indeed those clusters, those partitions become more homogeneous, and this is only a 2-dimensional projection. So even in 2-dimensional projection, you see this. But this is highly non-linearly separable. I mean, if I want to separate the black from the red here, I need to find a very funny and very complicated curve, even for this simple problem. Now, if I'm right, this representation of the layers should get better and better when I move to higher layers in terms of ability to decode the label. So, okay, so this is the first hidden layer. This is the fourth hidden layer in this particular problem. Look what happened during the same epochs in the fourth layer. So again, at the beginning, there's a strong bias to black. I mean, the offset is not yet set and so on. But eventually, even in this 2-dimensional scaling, you see that the red goes in one side and the black goes in another side. But you see something else which is quite remarkable. You see this dimensionality collapse. You see that eventually the manifold on which the layer lies is some low-dimensional manifold which is highly convoluted and highly folded in this space. But this is precisely this relevant dimension, which in this case is 1-dimensional. So you see that after enough training, the higher layers really represent this low-dimensional curved manifold of relevant variables, and all the irrelevant variables disappeared. They were forgotten. And so if you wait long enough, you really see red separated from black very nicely. So again, it's a highly nonlinear, but I can still almost separate them completely by one line. And you see this collapse of dimensionality. Eventually, the manifold goes to 1 dimension. So I actually believe that this is the picture in general. I mean, and actually there are many, and it's hard to see in high dimensions, it's hard to visualize in high dimension. But indeed what happens is that the irrelevant dimensions are disappeared because of the added variance to the gradients. Okay, so I have a lot of other things to say, but I think I'll stop here. So essentially, I argue that this information plane picture gives you really not only nice visualization, which is unique, it's some sort of an X-ray of the network, it's also giving us a lot of insight to understand what's actually going on, especially when you combine it with the, actually the summary is somewhat off, but never mind. If I combine it with the picture of the gradients, I get this very consistent picture that there's a first drift phase which is very fitting the label, and then a noisy phase which is essentially consistent with removing the irrelevant variables, and the reduction of the dimensionality because all the irrelevant dimensions eventually don't pass through the layers and remain irrelevant. Now, there are many, many interesting questions that come out of this analysis. I mentioned some already. I mean, okay, so can you predict the location of the layers? Yes, in some cases we can. In the cases where there is an exact symmetry underneath, and actually, all the problem I was actually using was I chose it very carefully to have an explicit O3 symmetry. So these are points on a sphere, and the label depends on some ratio of the dipole to quadrupole moments. So those of you who know something about spherical harmonics or something like this, this is invariant to rotation. And essentially what I argue that the layers in this case are going to collapse on irreducible representations of the symmetry. So this is a whole new theory which really relates learning to atomic physics if you want, but it's very nice. On the other hand, so this is directly related to the structure of the solutions on this information bottleneck curve. And I know that this irreducible representation, essentially water filling, like the Gaussian channel water filling, these are collapsed to low dimensional representation of the problem that preserve information. So this is just an extension of the Gaussian channels and Gaussian ray distortion problems to this. So this is one. The other thing is what can you do with for example, transfer learning. I mean, you want to learn one problem, and so I know already that the lower layers represent fine details of the problem. Usually they learn local symmetries, and the higher layers are really those global features. You see it very nicely here, because you see at what level of information they actually remember the problem. This has something to do with, okay, I want to move from one to the other. I want to learn from one data about another data. It also has some very bad message to neuroscience, at least if you believe that this has anything to do with neuroscience, is that neurons, but individual neurons actually tell you nothing. Actually, so I don't believe all these stories that you find in deep learning, you know, a face cell or a car cell or an eye cell or whatever. This is completely anecdotal. I mean, it's highly sensitive to the architecture. Of course, if you're using convolution neural networks and you constrain the receptive fields and you do all sorts of other things, then this scrambling of the layers disappear. But with fully connected network, you're not going to see it. But we actually have a complete theory of what do these layers really represent. And it has to do, again, with the structure of the phase transitions of the problem. But this is another talk. OK, so I'll stop here. Thank you very much. Just a little bit off time, but no. Yes, please.
It's still a little unclear why the optimizer that's just trying to minimize some empirical loss cares at all about empirical why does it end up being equivalent?
The empirical loss doesn't care about image information. It's the stochastic gradient descent that does. I mean, the fact that you use stochastic gradient descent, I mean, a noisy version of the gradient of the empirical loss. So first of all, the empirical loss that most people do use is actually the cross-entropy loss or the log loss, which is essentially mutual information, but that's a side, okay? But because you're using stochastic gradient descent, you get these two phases of gradients, okay? This has nothing to do with mutual information, okay? You get that you very quickly reduce the error on the labels, and then very slowly, when the error on the label essentially saturates, it's this noise in the gradients which all people think is random. It's not random at all. It's actually very informative. Now, what I'm telling you, okay, this is stochastic gradient descent. Has nothing to do with information. I didn't need information to tell you that. But now I look at what stochastic gradients actually do. I look at the dynamics of diffusion. And the dynamic of diffusion, using physics, is pushing us to maximum entropy distributions. Is losing information. So surprisingly, it's the dynamic of the stochastic gradient descent which is decreasing the information. So okay, so that's the connection between gradient descent and information. On the other hand, I showed you at the beginning of my talk that reducing information is improving generalization. So if I actually compress the input, by the way, I can compress the input by many different other means. For example, adding noise. So there's a very elegant work in computer science called stability bounds, for example. If your problem is stable to fluctuations in the inputs, then you generalize. What you think about its stability noise, if I add some little noise to the input and the label doesn't change, means that there's some sort of sphere around my patterns with respect to which I'm invariant, a label is invariant. So this is compression bound. The same is true about symmetry. If there's translation symmetry, rotation symmetry, or anything like this, it means that there are orbits of some class of transformations to which the label is invariant. And this is a compression bound, which means that there is a group of patterns which I can put together in one cell, which will have the same label. So this is, again, by the same argument, the number of labels that you need is much smaller. It depends only on the orbits of this group, and so on and so forth. I give you essentially any generalization bound, except those that are what we call, for problems which are strongly mixing, like parity functions, or like encrypted. I mean, whenever you have high sensitivity to noise in your input, you're not going to learn. Information theory is not telling you that, but you're not going to learn because you don't have this ability to compress the representation. If a single bit in your input is going to change the label, forget it. Deep learning will not learn it. So it's not a direct connection. The connection is between the physics and the dynamics of the problem, and then the miraculous fact that information theory is telling you something about typical behavior of large problems. So I'm using combining, it's just like, entropy and energy tell us something about the equilibrium state of matter here. It's not because the molecules calculate entropy. It's because entropy is describing the distribution for us. It's not an intrinsic property, it's a global. So it's the same story again.
So it arises as a side effect.
It's not a side effect. This is the right mathematics to think about it. But it's for the same reason, exactly the same rationale that the molecules in this room are very close to a Gibbs distribution subject on temperature and energy. It's the same rationale. It's not because the molecule calculate entropy. It's because this is the most likely or maximum entropy state of the system, and that's where we're going to find ourselves. Something very similar. I know it's not easy to digest, but think about it. More questions? Yes.
I was having a bit of trouble understanding what you meant by the first down. So you said that.
What I mean by what?
Your first down. You said that the sample complexity.
That's a very rough theorem. I completely agree with you. If you're unhappy with the mathematical formulation of it, you're right. What am I trying to say here? And of course, it needs. If we are working on it, we are writing a rigorous paper for information theory on this. Hopefully, you'll see it soon enough. But essentially, what I'm saying here is that these two numbers for the last hidden layer, which is essentially the point where you manage to put your last layer in this plan, is telling you both the generalization error, which is how much information you have about y, and the number of examples that you use, because you are converged to, essentially, it's this maximum of the red curve that I showed. So that's the argument. So because the maximum of this red, the compression is dominating the generalization error. I think I more or less argue that. And the information about the label is dominating, no, I'm sorry, the compression is dominating the number of examples, the sample complexity, and the information about the label is bounding the information, the generalization error. So it's these two numbers that really give you the whole trade-off. Now, the best trade-off that you can achieve is determined by the information bottleneck curve, which is essentially what is the most compression that you can get as a certain amount of information.
But the nature of information evolves
But
over time.
it stacks at some point. And this is the interesting part, and where it ends. So when you get to this particular value, you know that this is what you could do with this number of examples.
As in like at infinity epochs.
With infinite number of epochs. This is the convergence point. So if you converge to a point, look at the network. So if you look at one of those networks, I mean, I don't know, for example, those I showed you here. So it's the last point, this one here, or this one here. Look at the two numbers here, the number of bits here and the number of bits here. Look at how much you compressed the representation, and this tells you essentially what is going to be generalization error, and what was the number of examples that you had to use in order to get there. Yeah, I know it's not formulated precise enough, but this is the intuition. Yeah, I'm sorry. We get into the nasty question session. Sorry. Please ask me everything you want. I mean, yes.
Your examples went up to 6 layers.
Yes.
What happens if you go to 10 or 12 or 100.
Okay, so actually we did, I mean, this was a canonical example that I ran through this paper, but we tried it with different number of layers. So the real question is, what, if I'm right that essentially the number of layers is improving exponentially the convergence, so use infinite number of layers. So this is obviously wrong. First of all, you pay computationally heavily with this. I mean, there are many more promises, and then in order for this to make sense, I need enough space between the layers that they can actually move. And if you just use too many layers, then they're going to be redundant. I mean, most of them are going to have exactly the same position. You actually see it here. I mean, there are 6 layers, but you actually see only 4 or 5. And the 6th one is on top of the first one. So adding more layers is not going to change the picture dramatically. The question is, what does change the picture dramatically? And this has to do with the phase structure of the problem. So if you notice in my information bottleneck curve, there are those blue lines, which I didn't mention. Those blue lines are suboptimal solutions of the problem, which means there are different phases of the topology of the representation. And this is actually what I'm aiming at. So essentially, you don't need more layers than the number of different phases. Anything beyond that will be redundant. I mean, we do just another layer, which is a one-to-one transformation of the previous one. How do you know? Then usually there are many, many suboptimal solutions, unless you have symmetry again. If the problem is special or symmetric or simple, then those phase transitions, those suboptimal solutions really collapse to very few, and that's when the simple actually works so well. So our problem is symmetric, and I believe that this is why you see such nice pictures. In general, it's going to be a mess. I mean, just to give you some understanding what's going on there. In general, this bifurcation diagram is getting more and more complicated. And if there is symmetry, all those phase transitions or splits of clusters happen in the same places. This is actually the phase diagram of this particular problem, but you see that it's enough to put a layer between 2 major transitions here. So this is some sort of connection between the number of layers is determined by the really intrinsic structure of the joint distribution of x and y, which is determining these phase transitions. If you stay longer, I can show you much more about it. But it's a very good question.
One more question. We're running out of time. Go for it.
I'm sure it'll be short. If you don't have mini batches, what is the right way to think about the source of noise that still allows you to get generalization?
Yeah, okay, so that's again a tricky question. So first of all, I argue that the mini batches enhance the performance significantly. I mean, so you see again in this picture that when you increase the mini batch size, you actually shift the transition point because the noise is smaller. So what comes out of it is another interesting consequence or prediction of the theory is that the best mini-batch size should be such that the covariance matrix of the gradients, due to the mini-batches, is aligned nicely with the Hessian matrix of the minimum. Because then you're actually pushing in the right directions correctly. I mean, so these 2 ellipses, it's not ellipses, it's ellipsoids in very high dimension, but they should be aligned. If they're aligned, then you are most efficient. So there's a prediction here. Now, once you take full batch, I mean, you completely ignore the mini batches, the noise is there only for numerical reasons, for discretization of time, and indeed the whole thing is very, very slow. And if you see here, I mean, even for this with a full batch, you already get to thousands of iterations before you actually begin to see the compression. But eventually there is compression due to numerical noise. It's just not effective. So this is my prediction. If you choose first of all, learn with a lot of variability of the background. This is really important because this is what's going to give you a better stochasticity between the mini batches, which is going to eventually learn better. But now measure this variability of the background, actually the covariance of the mini batches gradients, and match it to the covariance of the problem. I mean, and in many cases, we can actually do this. This will enhance the learning. That's my prediction. This will be some sort of matching between the noise and the channel, in some sense, of this process.
Thank you very much.